2.5 Derivatives of trig functions. Today we're going to learn the derivatives of the 6 trig functions and just be able to apply those to all the other rules that we've learned, like the product rule and the quotient rule. And it turns out that the derivative of sine x is cosine x, and the derivative of cosine x is negative sine x, as you can see right here. So our first problem says find the derivative if y equals x sine of x. What you need to be able to see when you look at this is this is a product. You can think of this as f of x being x, g of x being sine of x. Since this is a product, you need to be able to come up with the f prime of x and the g prime of x, which we know. Next up, since we have a product, we have to use the product rule. The derivative of this is going to be whatever f times g's derivative is. If you don't know your product rule, you're stuck. Beyond that, it's just using the formula to plug in. Go ahead and try this on your own. And following our formula, we get our final answer. We get our derivative. The derivative of y with respect to x. Done. Next up, it looks like we have some kind of fraction, which should bring to mind the quotient rule. So maybe off to the side, you decide what's our f of x and our g of x, using our quotient rule formula, which says if we want the derivative of a fraction, we need to take the bottom times the derivative of the top, plus the top times the derivative of the bottom, I lie, minus, all divided by the bottom squared. So go ahead and try to fill in these 4 pieces. See if you get the same thing I do. Then we'll go on to actually using the formula. You should have gotten these 4 functions for your f, g, and their derivatives. Next up is plugging them all into the formula. First, I'm going to do it without simplifying. I recommend you pause the video and try that on your own. See if you get the same thing as me, then we'll simplify if we need to. There's definitely some simplification that can happen here. Looks like I can distribute my cosine of x. So I'll go ahead and do that. And negative sine x times negative sine x would be plus sine squared x, all divided by 1 plus cosine x squared. Now, you might think you're done at this point, but you're not. If you want to try to figure out what to do next, pause the video, otherwise I'm going to move forward. You should have looked at that and thought, oh, I know that equals 1. So the top now becomes 1 plus cosine x divided by 1 plus cosine x squared. One of the factors cancels out. We're left with 1 on top, 1 plus cosine x on the bottom. Now we're done. That's as simplified as it's going to get. Any questions? No? Good. Next up, we've got our other 4 trig functions, the derivative of tangent, secant, cotangent, and cosecant. You have to memorize them. There's no way to avoid memorizing them, kind of. You can kind of derive the formula for tangent by thinking of tangent as sine over cosine. Then if you use the quotient rule to find the derivative of this, you'll end up getting the derivative of tangent. So if you don't want to memorize these 4, you could always reinvent the wheel every single time. But I'm telling you right now, that's harder. It's better to just know these. Example 3 says find the second derivative at x equals pi over 4. You can't plug in your number until the final step. So you've got to find the second derivative first, then plug in pi over 4. So I start with f of x equals secant of x. First derivative is standard. You just have to have it memorized. We get it from right up here. Secant x tangent x. Now I need the derivative of that for the second derivative. And if you thought product rule, you thought right. Product rule again says if I want the derivative of a product, we do something like this. So taking a look at this particular problem, I'm going to take my g function, tangent of x, multiplied by the derivative of the secant function, which would be secant x tangent x, plus, I'll go back up to my formula up here. I wrote it wrong. If you caught me, good job. That second g f prime should be fg prime. Now I take my first function, which is secant x, times the derivative of tangent of x, which is secant squared x. We can clean this up a little bit. I see this as secant x tangent squared x plus secant cube x. And that's our second derivative, except we're not done. We're told to evaluate this derivative at pi over 4, which begs the question, what is secant of pi over 4? And what is tangent of pi over 4? Those are unit circle problems, so if you don't feel totally strong in your unit circle, pause the video, try to think about these. Don't just accept my answers. So we end up getting these values for secant and tangent. All that's left now is plugging these into the formula. F double prime of pi over 4 equals square root of 2 times 1 squared. That's nice. Plus square root of 2 cubed. So we have to clean this up. Looks like we have square root of 2 plus 2 square root of 2, which simplifies to 3 square root of 2. Done. To take this problem one step further, I might go ahead and say, now find the slope, or find the equation of the tangent line. And if you tried using this as your slope of the tangent line of the original function, you'd be doing something wrong. I'll leave that to you to think about why that would not be the slope of the tangent line of the original problem. It's not. I'm not going to tell you why. Think about it. Shouldn't be too hard. Next up, go ahead and pause the video and think about what you're looking at here. See if you can come up with a strategy. Hopefully you were able to look at this and think of a relationship between all the given information. We've got a theta, we've got an s, we've got a 50. This goes back to right triangle trigonometry, where we could say opposite and adjacent in a right triangle. Therefore, we're going to use tangent. And we know tangent of theta equals 50 over s. Except the problem's asking us to find the rate at which the shadow's changing, the length of the shadow, with respect to theta, which means we want shadow to be the isolated variable and theta to be like our x in a standard y equals f of x type problem. We got to get s by itself. So a little bit of manipulation, I'll cross multiply. S tangent of theta equals 50. So s of theta, or just s, would equal 50 over tangent of theta, or alternatively 50 cotangent of theta. Now we can find the rate of change at which the shadow is changing with respect to theta. Rate of change should give you the idea to take the derivative. So let's find our derivative. We know the derivative of cotangent. If you don't remember what it is, refer back to the previous slides. It would be negative 50 cosecant squared of theta. That's because the derivative of cotangent is negative cosecant squared. Next up, we need to plug in our variable, our number. We want 45 degrees, which is the same as pi over 4 radians. So we need negative 50 times cosecant squared of 45 degrees. we should be able to figure out what cosecant of 45 degrees is. I'll leave that up to you to verify if you don't believe me. Square root of 2. Square root of 2 squared is 2. 2 times 50 is 100, so negative 100. We're not quite done. We have to verify our units. It says express your answer in units of feet per degree. Well, it's giving it to us. Here is our y value, feet. Here is our beta value in degrees. So that's negative 100 feet per degree. Going back to what that's really saying in the problem, every time this degree changes by 1, you're going to get a longer shadow by less than 100 feet, meaning the sun's probably coming over this flagpole and causing the shadow to get shorter and shorter. Last example. Once again, go ahead and read this. See if you can come up with, well, you've got the correct equation, I can already see. See if you can figure out what to do with it before I talk about it. We're specifically telling you that this is the position function. We don't have to come up with an equation for it. It's asking you for velocity, and when we want velocity, we know velocity is a rate of change relating position and time. So if velocity is a rate of change, that means velocity would be the derivative of s, which we can find pretty simply. And it's asking us for the velocity at t equals 0. No, it's not asking us what the velocity is at t equals 0. It's just asking us to discuss what's going on. So if we look at the graph of the original function, which was s, that tells us the position at various times. So for instance, we start down at position -3 and eventually work our way up to +3, and then we loop back down and we keep going back and forth forever. It oscillates. And what's happening with our velocity during that time is we start off not moving at all, and we start speeding up. We get a faster and faster velocity. The fastest velocity we ever get is 3. Then all of a sudden it stops, which is reflected in the graph by having the velocity doesn't stop. The velocity gets fastest. Then it starts becoming slower, and all of a sudden we stop. Keep moving, but now the velocity is negative, so we're going backwards. And we're going backwards this whole time. The way that reflects in the original graph is our position is decreasing. When our velocity is negative, we should see our position decreasing. When our velocity is positive, we should see our velocity, or we should see our position increasing. And when our velocity is 0, we should see our position staying the same. This all makes sense in a physical world. Last up, go ahead and try these quick check problems. Come into class ready for some exciting trig. And tomorrow we get to learn about the chain rule.